So as a MR physicist, I think we're all professional artifact hunters. I see artifacts personally as I'm doing a lot of sequence development on a constant basis. And so as I try to debug where the artifacts are coming from, I start thinking, what kind of artifact is this? Where did it come from? How is it made? And so hopefully in today's talk, you'll be able to see how some of the common artifacts come about and some of the solutions for them. And before I get started, I just want to acknowledge some people for a lot of these slides, in particular, Jason Stockman, who's presented this, I believe, the past couple years and provided me with his slides. And he, in turn, used a lot of slides from Larry Wald, Todd Constable, John Polanyi, and Doug Knoll. And I also just want to mention some of the educational resources that I like to use, and I use in particular for making this talk. And so for anybody interested, they can take a look at these after talk to get more information on some of the artifacts that I cover and some of the artifacts that I don't cover just because there are so many to deal with in MR. In particular, I like MRIQuestions.com from Dr. Alan Elster. Has a lot of great material there. A couple of books I show here on the right. And also there's isomer educational courses on several topics, not just artifacts. You do need to be a member and to have a login, but you can probably ask a colleague to borrow there if there's any educational talks you want to see and get some more perspective about artifacts from other researchers. So with that, what is an MRI artifact? In the book MRI From Picture to Proton, it's simply defined as any feature in an image which misrepresents the object in the FOV. And so why does MRI have such a wide variety of image artifacts? Well, as you can see on the right, MRI requires a seamless integration and interplay of a whole host of subsystems, including the magnet, the gradient coil, the RF, and the pulse sequence computer. So if anything potentially breaks down along this chain, you'll probably get some sort of artifact in your image. Additionally, the human body also moves and interacts with the RF and the B0 magnetic fields. And these that provides additional source of static and dynamic physiological effects that will affect our final image. And so in order to understand where these artifacts come from, we have to know where to look. And the first place to start is within K-space. So it's important to remember that the raw data that we're acquiring is in the K-space domain. And so in order to get our final image, we perform a 2D or 3D Fourier transform of the image. So it's important to learn to think about what's going wrong with data collection in K-space, and then use the properties of the Fourier transform to see what effect these errors will create in the image domain. So I just want to give a quick sort of view of how we go from acquisition to image. So let's say we're running a basic gradient echo sequence that you see on the left through several combinations of frequency encoding and gradient and phase encoding gradients. We interrogate all the spatial frequencies that are present in our object of interest. We collect our raw data, the K-space that you see in the center, and then we perform the Fourier transform to get the image that you see on the bottom right. And so it's important to, again, remember that we're measuring a spatial frequency, and then we use the Fourier transform to get our final image. And the relationships that you see here between K-space and image space are very important to remember, particularly as we get into some of the artifacts later. So the spacing between points or lines in K-space, delta K, is inversely proportional to our field of view of the image. And similarly, the extent that we cover in K-space, the K FOV, is inversely proportional to the resolution, inversely proportional to the resolution of our final image. So it's very important to remember this inverse correlation between these two domains. And it's also very important to remember that each K-space point contains spatial frequency and phase information about every pixel in the final image. So as you can see, for example, the green square in K-space provides information on multiple parts of the image. And conversely, the red square in our image is made up of information from multiple parts of K-space. And this will become important. For example, if you see any RF interference artifacts, such that any small change, small intensity change in K-space can have an effect across our whole image. But I'll get to that a little later. Finally, I also want to show that in the center of K-space is our low spatial frequency information. So for example, if you were just to take the K-space that's within the red circle and Fourier transform it, you'll get this blurry view of an image. So it's clearly is missing a lot of the high spatial frequency information. And then conversely, if you were just to Fourier transform what's in the green circle in the top right, you get all the high spatial frequency information, which is related to basically the edges within our final, and all the details within our final image. So again, it's just important to remember how K-space is allocated as we're going through some of these artifacts. And this is unfortunately just a boring slide of some useful Fourier theorems to keep in mind to have a better understanding of what's going on in our final image. In particular, for example, the shift theorem in the top right, if you have a shift in one space, you'll have a linear phase change in your Fourier space. Also, the convolution theorem, the Fourier transform of convolving two functions is just a multiplication of the Fourier transforms of each function. And so these theorems are just good to keep in mind because they'll help explain some of the artifacts that we will talk about in a few slides. And finally, I just wanted to briefly show some of these different imaging encoding strategies that we have at our disposal. I believe Avery showed all of these in his talk a couple weeks ago, and I just wanted to reiterate all these different ways that we can acquire our K-space. And you can see all the different sequences associated with the Cartesian, EPI, spiral, and radial trajectories on the bottom. And it's just important to note how different the gradients are kind of operating for each of these strategies. And you know, that's just another aspect to keep in mind as you're thinking about why a particular sequence that you're running is causing a particular artifact. And so with that, I'll actually get into some of the artifacts, show some examples. So there are a great deal of artifacts that come about from hardware and acquisition, all the ones that you see on the left. I'm not going to go through all of them, but I just wanted to, I think these are sort of the main ones that we kind of think of as MR physicists. And again, if you're interested in more information about them or ones I don't talk about, you can look at some of those educational resources I talked about earlier. And so we have the hardware and acquisition artifacts. The other artifacts that we deal with, such as motion and chemical shift and stuff, are typically subject specific and harder to fix. So with that, I'll go into some of the common artifacts that we typically see. So for example, I think aliasing is probably one of the more famous MR artifacts. And so typically this happens when the K-space samples are too far apart, which results in a FOV that's too small. And so our image is wrapped around. And just to see aliasing simply when we don't sample enough, if you look at the example on the left, points A, B, and C are of different frequencies. And so we have enough samples to resolve the different frequencies. But frequency D, unfortunately, we don't have enough samples to resolve the high spatial frequency. And so it's mismatched to essentially to location A. And this is what happens in a sort of in 2D perspective. Again, if our K-space samples are too far apart, such as at the bottom K-space, then our FOV is too small, and you get these image wraps that aren't present when you have a full FOV. And so this is, you can see an abdominal aliasing artifact, and similarly what you see in the brain, where you have wraparound from the back of the head to the front. And so in many sequences, you can save time if you skip K-space lines and allow aliasing, and then use parallel imaging with multiple receive coils to unwrap the aliased image. And so this is typically under the IPAT tab and typically GRAPPA. So with regards to parallel imaging, so I assume anybody who's used the MRI scanner for any kind of brain imaging, for example, you're typically using the 32-channel receive array, and so we constantly use parallel imaging for a lot of our sequences to speed them up. And just a basic view of parallel imaging is that we have multiple receive coils that give information at sort of at a particular location within our field of view. If you can imagine this simple 8-channel example, you depending on where it is relative to the tissue, you get sort of more spatial information at all these different locations. And I'm not going to go into too much detail with parallel imaging reconstruction, but if anybody is interested, this review article by Deshmane et al. Is a very good resource that I have used in the past. So with parallel imaging, what we typically do is we skip K-space lines, and as I showed a couple of slides ago, if you were to do that under normal circumstances, you would get aliasing, and then you would get these wraparound artifacts, and your image is probably not going to be useful. But with parallel imaging reconstruction, which 2 of them I showed here, sense reconstructions and GRAPPA reconstruction, you can use the sensitivity maps from each of the receive coils that are present. Use that information along with the images from each coil, and then combine them in a particular way in order to recover our unaliased final image. But it's also important to remember that you can still get artifacts with parallel imaging, and just because you have, for example, 32 receive coils doesn't mean that you could accelerate all the way to like 30, you could do an acceleration factor of 32 or 16 or whatever. You're typically limited down to, in reality, depending on the amount of receive coils you have, probably R equals 4 maybe to get a usable image, although with newer reconstruction techniques they've particularly developed here at Martinos Center, you can kind of push that further. But in general, as an example here, this is with a 12-channel coil. At R equals 2, you have you don't really see any kind of artifacts, but when you go to R equals 3, you get noise enhancement, particularly in more in the center of your image. And this is due to the fact that our signal to noise ratio, when we use parallel imaging, decreases by our acceleration factor R, as well as the G factor, labeled as G on the bottom, which kind of describes the coil array and the different information you can get from each coil. So what happens if you have for example, if you have a coil that's just centered kind of, as you show on the previous slide, kind of around the edge, you get a lot of unique information along kind of the periphery and the edge of your brain, but each coil has the same exact information within the center. So the algorithm for unwrapping kind of doesn't work as well, and so you get these you get this noise enhancement, and you also get these residual aliasing artifacts as you try to push your acceleration further. So it's important to be mindful of what kind of acceleration factors are possible to get diagnostic quality images. Next, I want to move on to
before you jump on. There's a couple of questions in the Q&A. I think I'll ask you them in reverse order. So what does R represent exactly?
Basically, how many, relative to the full acquisition you do, how many lines you're essentially acquiring. So if you do R equals 2, you're only acquiring half of your K-space line. If you're doing R equals 3, you're only acquiring a third, and so forth.
Mm-hmm. And here's one I think you're probably ideally suited to answer as well. So why do we use multiple receive coils but not multiple transmit coils?
So, we actually, so in practice, for anybody that's scanned on like, Bay 1, Bay 4, basically particularly at 3T or lower, multiple transmit coils are rarely used. And one reason is because you have to be aware of SAR, so the specific absorption rate. And if you play pulse, if you have multiple transmit channels and you don't properly optimize it, you can get local heating, where you have kind of constructive interference, and so that could be dangerous. It's more challenging to use parallel transmit than kind of parallel receive. I think it's also more expensive, and it doesn't at 3T, for example, for 3T brain, I don't think I've really ever seen parallel transmit used, because you don't really need to, because the B1 field is pretty it's relatively smooth, but as you get to higher fields, and actually I do have an artifact towards the end that where parallel transmit is actually kind of the solution for. But parallel transmit, just, I've been kind of rambling, but is just more challenging and I think also more expensive. But if you plan on doing 7T stuff, that's where you're probably going to need parallel transmit. So anybody interested in Bay 2 might want to think about that. So that's about it. So I guess I'll go on. So truncation artifacts, also known as Gibbs ringing. Basically, if we just look at it, sort of this 1D example, if you're able to sample, kind of have infinite samples in your echo, when you do the Fourier transform, you get this nice rect. But when you start truncating your signal and you perform the Fourier transform, that's basically the same thing as, if you remember the convolution theorem I showed earlier, it's the same thing as convolving the Fourier transform of this sink, which is a rect, with the Fourier transform of a rect, which is a sink. And so you start getting these ripples in your sort of image domain here. And as you keep truncating it, you get more and more ripples. And the way this kind of 1D example transforms into 2D is basically when we don't acquire enough of the high spatial frequencies in K-space. So basically we don't go far enough out in K-space. And so at these kind of, at these edges, at these interfaces, you see these, you see clearly the Gibbs ringing. And actually this could affect sort of the pathology, what you kind of infer from the image. So if you have a small matrix size here, you get this pseudo-syrinx, which is actually just a Gibbs ringing artifact that disappears when you increase your matrix size and essentially sample more of the higher spatial frequencies. And this is very evident, which I have the pseudo-syrinx again here, but very evident here when you go from a matrix size of 64 to 128 to 256 to 512. At 512, it's, the artifact is it's very nearly gone. As an alternative, you can also filter your K-space data with the smoothing decreasing window to try to get rid of these truncation artifacts, but typically I think increasing the matrix size is easier, although at the cost of increased scan time. So zipper artifacts come about from RF interference, and they usually show up as these lines along the phase encode direction. And typically that is an indication that the room is not properly shielded, or the door is not fully closed, so you get some RF interference that kind of sneaks into the scan room. Alternatively, there might be an RF source in the room. So electronic devices, I think like pulse oximeters, things like that can unfortunately create some RF interference. And I imagine in those situations, it might be a little more difficult to get rid of. So you might have to live with that. But truth be told, I haven't really experienced this artifact, or very rarely. But it's just something to be aware of, how RF interference can affect your resulting image. Another similar artifact is just a simple spike within your K-space due to RF interference. And again, it's important to remember that this little, you're going to have this inverse relationship between K-space and image space, where this tiny little increased intensity shown with the white arrows results in this huge artifact in your image space after you do the Fourier transform. And if you have multiple spikes, as you can see with the 3 white arrows on the right with an actual abdominal image, you get this herringbone artifact, which is basically just these different patterns that you kind of see on the link and combining to get these kind of like crosshair kind of artifacts. This one, again, you just want to make sure that the RF shielding and the door is closed and all that, and there aren't any sparks or other electronic devices that could affect your scanning during the data acquisition. If you ever see a spike like this, you have this bright intensity in one of your K-space pixels, I think you can just set it to 0 to kind of get rid of it, and hopefully you'll still get the image you expect. But this kind of comes about. Do we want to save questions for, I don't see the Q&A, but I see there's a question. Do we want to save it for at the end or answer them as we go?
I think as we go. This question was, are these K-space images in log 10 scale? Or log scale?
No, I think these are, I don't think these are log scale. I think it's just you have this very bright pixel that certainly stands out, that creates this artifact. Yeah.
Okay.
Yep. Is there another question, follow-up question?
Yeah. Do you know why there's these bright lines along KX, like along the axes, like the KX and KY equals 0 in the K-space?
Oh, why K-space is brighter here than it is in the...
No, along the axis lines, like the entire...
Oh, along the axis lines. So typically the lines at the center of K-space is usually when the gradients, I guess one or both in the case of the center, are 0. So typically you get the most signal in the center. You typically get the most signal in the center of K-space, and along these center lines of K-space, along the center lines of these K-space as well. With yeah, I don't know if Avery, if you want to add anything.
Yeah, I guess in this case, I feel like there must be something in like there's something in, I mean, the Lincoln images weren't acquired with MRI.
No.
There must be some feature in the images that are very strongly horizontal and vertical, so that they're showing up at all horizontal frequencies and all vertical spatial frequencies. Like maybe there's a border or some border in the image that's somehow factoring in there. I'm not sure.
Yeah. I guess it just depends on the spatial frequency content in the end of the image that you're looking at, or the object that you're interested in. And so I think that's the easiest way to sort of think about how K-space is being filled for a particular object. Kind of break it down, but what kind of spatial frequencies you'd expect with the center of K-space being smaller spatial frequencies, so corresponding to kind of the coarse objects, the coarse portion, and then the high spatial frequency is kind of as you go out, kind of in the diagonals.
Yeah.
So
I think there's another follow-up question, but I think for the sake of time, we should just move on and suggest that people can easily calculate Fourier transforms in MATLAB, like with FFT2 or FFTN or something like this. And just feel free to play around and see if you can figure out some of these different features yourself in different images.
Yeah, and also I'll have my email at the end of this. So if you have any follow-up questions, feel free to email me, and I'll email you back, and hopefully point you in the right direction to get more information about this. So, um, so another thing, another artifact come about from eddy currents, which are such a magnetic field that creates these unwanted currents in other nearby conductors within the bore. So you can kind of see that on the right, where you have an electromagnetic field being created by the coil, and it's creating these eddy currents in nearby conductors within, for example, if you're in the bore, and so what these eddy currents typically do is they'll kind of screw up the intended gradient waveform that you want to play. So for example, if you assumed you were playing this nice rect gradient with eddy currents being present, your gradient waveform is actually distorted, and so that'll certainly mess up how K-space is being filled. And typically we don't worry about eddy currents since the manufacturers typically have eddy current compensation present. So for example, if they know that this is the type of eddy current that'll kind of be playing, they'll actually input the gradient waveform with this pre-emphasis modification, and ultimately you'll get the gradients that you want. So you don't have to totally think about them, but they are present, and they typically come up in like D0 mapping. They could play a role, and it's on the next slide, but these eddy currents, yeah, they typically create these distortions that are direction dependent. And typically you see them with the fast switching gradients, which are very important in EPI and diffusion sequences. And so depending on the direction that the eddy currents are occurring, you can have this global shift in the B0 direction. You have this image shearing if it's along the readout direction, and you can have this image scaling if it's along the phase encode direction. And another reason eddy currents are very important just to keep in mind is because of the ghosts that they can create when running EPI sequences. So in EPI, it typically uses bipolar readout gradient. And so these even and odd lines of K-space that you kind of see in A have this out of phase, have the echoes kind of out of phase. And so when you have this phase issue, when you do the Fourier transform, you get these ghosts. So this with the n/2 ghost, which is a half of field of view shift. And so yeah, again, this change in this phase error in K-space causes this translation of the image within the image domain. And so just if anybody's running EPI, it's very sensitive to hardware instability because you're playing these fast switching gradients. So it's nice that it's a very fast sequence, but unfortunately you can have these ghosting artifacts. But typically for, I think the sequences provided by Siemens on the scanner, they do a ghosting correction for you, so you don't really have to worry about it in the end. But in case you do still have some ghosting within your image and you're running an EPI, it's worth understanding where they're coming from. Typically it's eddy currents, and it could be other issues as well. And you can do some of this ghost correction offline. There's a lot of literature on this, but again, just something to be aware of. And then I also quickly want to mention some of the non-Cartesian artifacts. So, I showed those 4 basic image encoding strategies earlier. So Cartesian, EPI, we just talked about, the ghosts that can occur. And then I also talked about radial and spiral that are becoming very very commonplace more and more. And in terms of the artifacts you get with spiral, you can get some blurring, and you get these sort of diffuse artifacts that you can kind of see these streaks depending on how many radial views you use in order to acquire full K space. But these artifacts are just kind of different than what you expect in sort of Cartesian, typically line by line acquisitions. So you get these diffused artifacts, and you actually get this kind of, you can still get this aliasing that's actually kind of has this radial aspect to it. So just something to keep in mind, between this and the previous slide, kind of knowing what sequence you're running, so then what kind of artifacts you might expect from them. And then another thing I just wanted to quickly mention is the concept of gradient nonlinearity. So if our black dot represents an isocenter, the gradients are kind of linear within a certain range, and then they start to fall off. So what you might have, if you don't have any correction, if you look at A and B, is this clear distortion within, particularly within your image at these edges. You get this the distortion of your images, but and that typically only depends on the gradient coil. It's the same for any object, the same for any pulse sequence. And the solution is as simple as it sounds, is to correct for nonlinearity, but that's also typically done for you on the scanner. I think the vendors just provide, they know what gradient coil is in there, so they'll do the nonlinear correction for you. And so if you do the correction, you certainly get a better image than without the correction. So again, just something to keep in mind, but this is also done for you by the vendor. And so I covered a lot of the hardware acquisition artifacts. Some that I didn't cover, like receiver dynamic range and central point artifact. Again, if you're interested, take a look at mriquestions.com, and they'll have information on that. And so I just want to cover just some of these artifacts that you get in a subject-specific manner with the human body present and the interaction that are there. So motion artifacts, probably anybody who's scanned a lot of people, you probably come across them. So motion causes phase errors in the data, which leads to a misregistration in the phase encode direction. Periodic motion leads to ghosting. These shifted images that can constructively or destructively interfere with the primary image. And so some of the solutions, which I'll also provide later, you can correct for the motion-induced phase errors. You can do some fast imaging, or you could try to follow the motion and I guess try to correct for it. To just quickly understand motion, we could take a look at this 1D example. So you have your original K-space data, and if you multiply it in K-space by this periodic modulation, that's equivalent to convolving kind of your resulting image. Let's say you have this rect, convolving it with the Fourier transform of this sine wave. You get these delta functions, and so you get these ghost images in the image domain. And so luckily, in here, the ghosts are separated in this example, but in reality, they usually overlap in practice. And so before I just leave the slide, I just want to remind people the convolution theorem that I presented earlier is a really helpful way to look at this, where you're multiplying two functions in K-space, and that results in a convolution kind of in image space. So if we look at a 2D acquisition, you're acquiring your data, everything's fine. You do your 2D FFT and you don't really have much motion. You get the image that you want, but now you've introduced this periodic motion that results in a phase error along the phase encode direction, which is vertical in this case. and you start getting these replicates, these ghosts of your of your object, and it can get really, really severe depending on how much motion there is. And in some cases, these phase errors may only occur for only certain voxels, only the ones that are actually moving. So just as an example, you can have a motion artifact from flowing blood on the left, which is periodic due to pulsatile nature of flow. So you only get it here in the phase encode direction, kind of up and down. The image you saw previously, it's from a beating heart. Then you can also get a motion artifact from breathing. And then, you can get a motion artifact that completely goes off the rails, and basically the entire object is included as an artifact, kind of this bulk motion. And just so you could have different severity and extent of artifacts. You can try to do some motion correction here. You have no motion, then no motion with motion correction. Then with motion, you can clearly see this corrupted image, all the kind of ghosting that's overlapping. But with motion correction, you can then get back your original image. And there's a lot, again, in the literature about motion correction. There's some interesting stuff being done here at the Martinos Center with Steve Cawley and Larry Wald. So if anybody's interested, you could take a look at the literature. And really, there's a lot of motion mitigation strategies. With regards to respiration, you could have gating and triggering. Similarly with the cardiac, you can gating and triggering so that you're acquiring only at certain points to minimize the motion. So it's just be a longer sequence, but certainly helps. And then another thing you can do is, instead of running a Cartesian acquisition, as you see here, you get these artifacts. Instead, you can do a radial acquisition that kind of has these, again, as I showed earlier, these more diffuse artifacts, and it also averages out the motion because of the variable phase encoding technique, and it also oversamples the center, so you can use that information to try to correct for the motion. So that's just another strategy that's been implemented, and I think spiral and radial acquisitions are used a lot in the body. I think spiral in particular for the heart. So that's motion. And then kind of another artifact that you commonly see deals with the chemical shift. So fat and water resonances, they move in and out of phase over time because water processes approximately 3.5 ppm faster than fat. So, as you, at these different kind of echo times, these different times, you can see water, the fat going kind of, it's in phase with the water, out of phase with the water, in phase with the water, out of phase with the water, and so forth, depending on the times. And this is typically exploited to help produce fat and water only images. So anybody that's run any kind of Dixon scans, you can set it on the scanner to provide you with the fat images on the left and the water images on the right. And the way this is actually calculated is you get, if you choose an appropriate echo time, you get an acquisition where fat and water are in phase. And if you do a second acquisition, you get a second echo time where they're out of phase. In order to get your water image, you can combine these images so the fat will cancel out, you get your water image. And then similarly, if you subtract them, the water will cancel out and you'll get your fat image. So, you can really, chemical shift might be an artifact that I'll show on the next slide, but it can also be used to help separate fat and water. But an issue does arise where the fat, if you have your water, if your center frequency is set to water, and so fat is then sort of mismapped as kind of as water resonating at a slightly lower frequency. So you get this, you get this shift of the fat. And what that does to your image is that you get the signal void, where you get destructive interference of the fat and water. And similarly, you get this overlap where you get brightening, where the fat and water are kind of occupying the same voxels. And so you get this signal intensity that, you ordinarily don't want to see. This is also illustrated on the left, where the most important thing is to look at the fact that, with the high receiver bandwidth and high resolution, you don't get any chemical shift artifacts. But then if you were to decrease your receive bandwidth, you start seeing this artifact in the readout direction. Sort of, you can see here. There's a question. I don't know. I can try to answer it now.
I think for the sake of time, we should just go through the rest of the lecture, and then we'll answer questions at the end for people that have questions.
Yeah, and again, feel free to email me if I don't get to it.
Okay.
Yeah. Oh, yeah, and so just another, you can see this. If you have a low readout bandwidth, you have this brightening here, and if you have a higher enough readout bandwidth, you have you don't have this chemical shift artifact. And actually, if anybody, if you look at the bandwidth setting on the on the scanner itself, and you kind of go over it, the sequence will tell you, depending on how many frequency encodes you have, and what your bandwidth is, what kind of shift you might expect. So you can actually calculate kind of how many pixel shift you would expect. So it's actually kind of helpful to know if you see this value and you don't like it, and you should, you could try to increase the bandwidth if possible, or play around with other parameters to kind of decrease its chemical shift artifact. And interestingly, in EPI, I just want to mention real quick that the chemical shift is actually in the phase encode direction, because the phase encode bandwidth is it's really low. And so, at 7T, depending on what your echo spacing is, and so forth, you can get a 38 pixel shift. And so I think it's very important to have fat saturation on, so that you kind of eliminate this artifact. So it's just an interesting thing that it comes up with EPI. It's in the phase encode direction. So just something to keep in mind, again. And then I think one of the last things is talk about just, sources of in vivo B0 inhomogeneity that might occur. So typically an empty magnet is shimmed very well, but when you put a person inside, you get these air tissue interfaces that can perturb the B0 field by a ppm, and so this typically occurs in the sinus and oral cavities and in the ear canals for anybody doing head imaging. And then you can also get these dynamic B0 shifts with the respiration. I kind of showed that earlier, and other physiological processes. And so, you have these variations in B0 in your object of interest, and that's going to create some artifacts as you're scanning. For example, with metal implants, are kind of a very extreme case. If the difference in like air and tissue is only a 1 ppm, then when you have something like a hip implant present with titanium, that's 182 ppm. So you have a rapid changing B0 field near near your tissue. And so this, kind of creates a severely short T2 stars near metal in the body that causes dephasing and signal loss in gradient echo. You can clearly see this dephasing with dental, metal in the brain, and you get this kind of blooming artifact. If you're running this just 2D fast spin echo because the RF excitation and refocusing pulses don't work properly. And so there have been special techniques created in order to overcome these, where you basically acquire several different frequency offsets and then put them together in order to eliminate this artifact and get the signal from the nearby tissue. So, but then this static B0 issue really comes up at higher field at 7T. So this is work from Jason Stockman here, who clearly shows here, you have these large delta B0s over here, I guess, near the sinuses and stuff. And so depending on what kind of resolution you're using, you'll get, and you want to do some T2 star imaging, you clearly get this loss of signal here that can kind of be improved with a higher resolution and smaller slices, but it's just something to be aware of, this delta B0 problem that occurs at 7T. You also get this through slice dropout with the gradient echo EPI slices. So you can see if you have a 6 millimeter slice, you have this large intravoxel dephasing causing this loss of signal. But then as you kind of bring down your slice, down to 0.75 millimeters, you kind of recover signal because you have less dephasing. And again, you look at 7T, you can get some of these, you can get some shifts in signal. You can get this geometric distortion that occurs. You can see the worst B0 as you go to 7T. So, one way to help this in particular is with the parallel imaging to reduce the effect of echo spacing, and that helps kind of get your signal back. But again, just something to be aware of at high field. And lastly, I think what you talked about earlier, this concept that you get this B1 inhomogeneity that occurs particularly at 7T. In the brain, you can see this central brightening artifact. You look at these B1 plus maps, you get artificially high signal due to constructive interference. And similarly, you can see this destructive interference that occurs at 3T in the abdomen. And so typically, one way to overcome these is to use a parallel transmit in order to kind of play the right pulses with all your different transmit to not have this constructive and destructive interference and to get a smoother B1 field. And so just before I end here, we get to the quiz real quick. When you're dealing with artifacts, as you're going in, it helps to know what to expect. So you could probably, based on what you're running, or they've shown here, you can probably predict what kind of artifact you might encounter. And just think about, does something look wrong? Is something missing? Is there an extra something? Is it mimicking pathology? Do you totally care about the artifact? Perhaps something's folding into an area that you don't really care about, so your image is still useful. Then can you explain it? Can you remove it? And perhaps maybe there's a way to use it as well. So. And finally, there's this slide I just recently found in the Picture to Proton book that kind of goes through, this nice flow chart of how to figure out what kind of artifact you might be getting. So, I haven't taken a look at it too closely, but it certainly looks very helpful if you're ever stuck in trying to figure out what could be causing it. So, I think that's it. So. I don't know if we still have time for the quiz. I could just go through.
How about we pick like 2 of your favorites, then we just launch those.
Yeah. All right. Well, trying to remember. This one wasn't my favorite, so.
Okay.
But yeah, this was just a Gibbs ringing, similar. We could do this one real quick. You can see you know, these images from a patient, these spin echo and gradient echo images, and so what kind of I guess artifact are you particularly seeing in the gradient echo image? So it's a T2 star dephasing from metal object. I think you can see what I think is a clip. I'm guessing an aneurysm clip here. That you know, the spin echo is not as bad, but in the gradient echo, it's much worse. You get that dephasing because of the rapidly changing B0 field near the metal, the susceptibility artifact. And I guess there's no easy solution, but maybe you could run some of those special sequences to try to overcome that, or use a different sequence. Don't use a gradient echo. You have the fat water shift along the readout direction. So basically just a chemical shift artifact. You get the darkening near this interface where there's, you know, voxels that contain both fat and water, dark over here, bright over here. So probably to fix this, you'd want to increase your readout bandwidth. It's probably the easiest thing to do. So yeah, I think that's it. I guess we had one more, but I'll just let you know. So, you know, you get these geometric distortions that that Jason Stockman has been working on, creating a special coil to help improve the shim and basically just improve ultimately your B0, which significantly improves the images. So if you're interested in this and need some help with this issue, talk to him. He'll be happy to help, I'm sure. With that, I'll just leave you to say that this artifact that I showed at the beginning was iron oxide suspended in beeswax hair product that causes these kind of susceptibility artifacts. So pretty cool. Thank you. And if you have any questions, feel free to email me, you know, and I'll help you out as best I can.